Okay, here we are. This is the video lecture 4 for Physics 2A. Physics 2A video lecture 4. And these lectures are for both sections of Physics 2A. Let me encourage you to take good notes and watch all of these videos. So the videos will always be posted by the time class would have been in session. Both classes, so Tuesday, Thursday, and Monday, Wednesday, Friday. So they'll be posted on time. And this is the 4th one, so make sure you get good notes for all of them. And let's begin. So what do I have here on the table? I'm going to wrap up chapter 8 today. Got a gyroscope, got the bicycle wheel, and I want to start with this demonstration. And really, this is one for you guys to just think over a bit. So I'm going to start these guys rolling down the hill, okay, rolling down the incline, and they're designed to have the exact same radius and the same mass, and the difference is that the holes have been drilled out at the outside on one of them and towards the inside on the other. And now if you think back on the rolling races I showed you last time, you may realize one of these is going to win the race again. Okay, but which one is it? Which one? Give it a little moment, think about it a bit, stop the tape, think about it some more. Here goes the demo. On your mark, get set, go. Blue for the win. Blue for the win. I'm going to go ahead and do a second one. Switch them out on the different tracks just to make sure there wasn't something going on there. On your marks, get set. This is nice because the whole episode is slowed down a bit. Blue for the win. Okay, does anybody know why? Well, let's think about that. It has to do with the moment of inertia. Which one of these has a greater moment of inertia? All right. Next thing I'm going to do, I'm going to demonstrate the gyroscope. Here we have a pretty high quality gyroscope, and I have an interesting demo with the bicycle wheel. We'll do that later on. Right now we're going to review our homework. Review the couple of interesting homework problems that we had. Let's just get this out of the way. Okay, let's see what was on the homework. I'm thinking of doing, well, let's write down what the homework was. We had $839, $845, and what was the third one? $858. Now 39, I'd say was pretty trivial, but a good start at the whole concepts. 845 is interesting. So let's talk about this one next. So problem 845, we've got some merry-go-round, we wrap a rope around it, give it a big pull and spin the thing up. So we're spinning an object up, and that must be a case for this equation, I alpha. And I'm not plugging any numbers in, and you'll see why in a moment. So yeah, the top view of that merry-go-round is this thing here. Okay, we're spinning it up, and it has a radius r, and we've got a rope attached, and we're pulling this thing, and it's going to start rotating. Okay. It has a mass, it has a radius, from which we can get the moment of inertia. The moment of inertia, we're just going to think it's a big disk, so I is equal to 1/2 mr². Okay, another thing that's going on is that we're going to use omega equals omega 0 plus alpha times t as the kinematic equation. The kinematic equation, we're starting from rest, so we can say that alpha is going to be omega over t because they gave us a final omega and they gave us some seconds in time. Some seconds there, okay? So now let's evaluate this expression. The torque is the force times the lever arm, which in this case is the radius of our merry-go-round. The moment of inertia, we know we can get from that right there, from that expression there, and the alpha we're going to get from this expression here. So let's go ahead and see what we have there. We have 1/2 m r squared. Be careful, I'll separate the numerators and denominators like that. Mr squared over 2, that's a 1 right there. Mr squared over 2. And what do we have for the alpha? We have omega over t. So we're equating these, and we see that there's an r that's going to cancel from here, so we're going to end up with the force is equal to mr, cancel one of those, omega over 2 times t. And now we would plug in numbers. Okay, now we would finally plug in numbers. There's one more thing I wasn't that pleased. Well, that's fine. The thing is that we had omega was 0.5 revolutions per second. And what we do is we convert a revolution to 2 pi radians per revolution. Revolutions cancel. And so 0.5 times 2 is 1, and so what we actually had there was pi radians per second. So that's what we would plug in for the omega. The t was given, mass was given, the radius was given. There's our answer. Okay. That's a pretty interesting problem. Bringing a few things together. Kinematics, the dynamical equation, the moment of inertia, it's bringing all kinds of stuff together. Okay, excellent problem. So systematically, we were working with Newton's law of revolution. Is that what his law is called? Newton's law of rotational motion, let's call it that. There we go. Okay, so that was problem 845. What else did we have here? Problem 858 we'll do next. This one was also actually a different version of one that I did at the board. And I'll prove that to you next. So let's do 858. Erase this. Yeah, here we had a bucket attached to a spool of mass m and radius r, so that's a disc with string around it. Maybe we'll use some blue ink for the string just to make this a little more colorful. Strings wrapped around, connected to a bucket. And bucket here, it's got a handle. All right, and we'll say this has mass m. Now I set this one up with the dynamical equation, but this time we're supposed to do energy. And namely, we're going to release it from rest, and then it's going to drop a bit in a dotted line. It's going to end up down here. And therefore I can say this is the A point and this is the B point. We're releasing it from rest at A, it's going to spin on down and descend, and down at B it's going to be moving. And we want to know what is omega of the spool at B. So how fast is the spool rotating when the thing has made it down to point P? Okay, we have our technique for these kind of problems. By the way, here's the axis of rotation. We say E sub A is equal to E sub B. And the energy referred to the height difference. And that height difference we're just going to call H. And so it was all potential. So we just had the bucket, which is the one that's moving, MGH, and it's moving up and down. So that was at the beginning of our situation. At the end, that potential energy is used up, but this one is spinning and this one is moving. Both have kinetic energy. So 1/2 mv squared is the kinetic energy of the bucket as it's moving down, and 1/2 I omega squared is the kinetic energy of the rotating spool. So this is a very similar expression to our rolling rates. Okay. Similar problem. And from the kinematic equation, we know that V is equal to omega R. So that's what we're going to have to plug in here. Or omega is equal to V divided by R. In this case, we're using this equation here. So here goes. MGH equals 1/2 mass of the bucket omega R quantity squared plus 1/2 I, which is going to be 1/2 mass radius squared for the disk omega squared. Okay, I'm just going to put a box around this equation. So here you would have done all of the physics. The remaining step would be to solve for omega. And then, then you're plugging in and you're factoring omega out, omega squared out. And so factor out, and I'm just going to write solve for omega. So that would finish this problem up, but here we've set it up and actually done all the physics. You factor out the omega squared. You'd see there's common mr squared, 2, 4, etc., etc. So you're not canceling. You're not canceling anything here so much as you're just factoring out, solving for omega squared, and then once it's as simple as you can get it, then you plug in your numbers. Okay, good. So that was problem 58. So we've done both of these, and they cover a lot of ground. I like the energy method. And we have all the rotational quantities that we're talking about right here. So now we're going to move on. We're going to move on to, let's see here, erase everything. Here, I'll put this up before I erase. We're moving on to angular momentum. Next, angular momentum. This is a development that is parallel to the linear momentum and conservation of linear momentum that we had discussed in chapter 6. So, and it's actually a much richer set of phenomena, actually. It's quite amazing. So let's get a look at that. Angular momentum, I first want to bring the bicycle wheel into play here. Let's talk about this a bit. When I spin this thing up, we're going to find it has what's called angular momentum. It's rotating, and the moment of inertia plays a big role here. This bicycle wheel, if you were to lift it, it's actually quite heavy.